Okay, today I'm just working through some ideas on how to calculate kinetic energy spectrum for 2D velocity fields in irregular geometries. Basic idea is we want to write a vector field using a Helmholtz decomposition. So we have u is grad chi plus z hat cross grad psi. There's two Helmholtz potentials, chi and psi. And this form is nice because we can take the divergence of u and get an equation only for chi, and we can take the vorticity of u. So it's the divergence of z hat cross u in 2D, and we end up with an equation only for psi. These equations are the field equations for these Helmholtz potentials, chi and psi. To completely specify this problem, we need boundary conditions. And we have, the way we derive boundary conditions is we have a domain. Here's what it looks like. It might look something like this. Might have some little islands in there. Put a little arrow here to indicate what we call positive direction. So this guy's got outward pointing normal, n hat along the boundaries, and a tangent vector along the boundaries. Okay, n hat and t hat. And on this boundary, the velocity field could be anything. And this happens a lot in regional simulations of the atmosphere or the ocean. And we know what the velocity field is in the tangential direction and in the n hat direction. And if we use the Helmholtz equation there, we got grad chi dotted with t hat. Then we have z hat cross grad psi dotted with t hat. So let's work that out real quick. I'll use a different color here. So this term, what we're working out here is z hat cross grad psi dotted with t hat. And we need to relate n hat and t hat because they are related to each other. You know, if I give you n hat, if I rotate 90 degrees counterclockwise, I can get t hat. So if we say n hat is nx in the x hat plus ny in the y hat, t hat is going to be, the way I like to figure this out is I know that if I'm pointing in the x hat direction, t hat, so if this is n hat here, t hat is going to be in the positive y direction. So what we end up with right now, if I do n hat in the positive y direction, then t hat's going to come down to the negative x hat direction if I just keep going counterclockwise. So what we have is this guy's going to be minus ny in the x hat plus nx in the y hat. So we know those rules. Okay, those are given. Z hat cross grad psi, what that is minus d psi dy in the x hat, and then d psi dx in the y hat direction. So if I do that, So z hat cross grad psi dotted with t hat. I'm going to get psi y ny plus psi x and x. Okay. This is just grad psi dotted with n hat. That's all that is. So I can replace that. Just makes it a little bit easier to work with, in my opinion. Okay. The next one, we have u dot n hat, grad chi dot n hat. And again, we're going to get z hat cross grad psi dotted with n hat, but we need to, we can express it in terms of t hat here. So what we get is minus grad psi dotted with t hat for that term. So that's nice. So we have some requirements of how we could match up gradients of these potentials on the boundaries. There's a lot of choices you can make. And it's not unique. This is a known thing with Helmholtz decompositions. This ambiguity in the boundary conditions is not unique. So we can make a choice, make any choice we like, so long as we meet these requirements. We match the tangential component and the normal component of the velocity field on the boundaries. So, one choice, so we'll say one option, option one, is to let grad chi dot n hat equal u dot n hat. If I make this choice, what follows because of this is that grad psi dot t hat has got to be 0. Now, physically what this means is that the rate of change of psi along the boundary has got to be 0. And that's along every boundary, right? So that means psi is a constant. I'm going to introduce some notation here. And I'll do this in green. If this domain is called A, then the boundary we're going to call, it's written as partial A, but that's boundary of A. Down here, this is on the boundary of A, on the boundary of A. So psi is a constant. It's not necessarily 0, but it's a constant. Okay? So that's one choice. We could choose to set the normal gradient of chi, which is the divergent part of the Helmholtz decomposition. If we choose that, then we get psi as a constant. And you can see I could pick any number of things here. I could say grad psi dot n hat equals u dot t hat, right? Which means that chi would have to be a constant on the boundary. That's another possibility as well. There's a lot of options, right? We can pick any linear combination of these things. We're going to stick with option 1 here for now. So if I choose option 1, let's restate our problems here. We have del squared chi is d, and we have grad chi dot n hat on the boundary of A is u dot n hat. Okay, so that's for the divergent part. For the rotational part, we have del squared psi is the vorticity, and we have that psi, and I'm going to get even a little bit more complicated here. We're going to call the outer boundary delta A 0, and then all the inner boundaries will be delta A 1, delta A 2, delta A 3, right? So we could have, let's say, n of these. So let's say n plus 1 boundaries. Okay, so because we got the 0th boundary and then n interior boundaries. So psi on boundary AI, we'll say is Ci, so it's a constant. And like I said, it's not necessarily 0. We had a very simple scenario where we just had just the outer boundary. We could choose that constant to be 0. And in the problems we'll do in a little bit, that's what I'm going to do. Okay, so we have the problem definition. Now, I'm trying to calculate kinetic energy spectra, so let's talk about how we calculate kinetic energy. So the kinetic energy, if this is a velocity field, like a velocity field for a fluid, is 1/2, and I want the total kinetic energy, so I want the area integrated kinetic energy. Right. It's going to be u squared plus v squared dA. So integrated over all the space. Now if I have that u is grad chi plus z hat cross grad psi, so if this is my definition, what this means is I have the derivative of chi with respect to x minus derivative of psi with respect to y in the x hat direction plus derivative of chi with respect to y plus the derivative of psi with respect to x in the y hat direction. So this is u. Okay. And this is v. Okay. So if we have that, u squared plus v squared is going to be chi x squared minus 2 chi x psi y plus psi y squared. That's the u squared part. And then we have v squared, it's chi y squared, 2 chi y psi x plus psi x squared. Okay, so we can combine some terms here. So these guys together give us the magnitude of grad chi squared. These two give us the magnitude of psi, grad psi squared. And the remaining terms give us 2 grad psi crossed with grad chi. Okay. So altogether, we can write the total area integrated kinetic energy as grad chi squared plus grad psi squared plus 2 grad psi cross grad chi dA. Okay. I'm going to show you how we can use those boundary conditions we came up with before. Kind of helpful here, because what we can do, those boundary conditions we can use to show that this contribution to the integral goes to 0. This is nice. So, what we're interested in is this term, the area integral grad psi cross grad chi dA, which we can write in one of two ways. We can either write it as the curl of psi grad chi or we can write it as the minus curl of chi grad psi. And we can use Stokes' theorem to convert that area integral into a boundary integral. Notice the closed loop there. And this becomes psi grad chi dotted with tangent dl or we can write this as boundary integral chi grad psi dot t hat dl. No matter what I do, these two integrals are equivalent to each other. Okay. So we chose the one boundary condition. Remember our boundary condition. Our boundary condition says that grad chi dot n hat on the boundary is equal to u dot n hat. And we have that grad psi dotted with t hat is equal to 0. So immediately we could see if I plug that into the second form, this is 0. The other one's a little bit trickier, but because psi is a constant, I can pull it out of the integral, and I'm left with grad chi dot t hat integrated over a closed loop. Now this is just the derivative of chi along the boundary. So grad chi, or derivative of chi with respect to L, this is the boundary length, dl, and so this is, in other words, just the change in chi along the boundary. And since it's a closed loop, as long as chi is continuous on that closed loop, which I'm going to assume it is, this is 0. So both of these integrals evaluate to 0, which means this is 0. And it turns out that works for any of the boundary conditions we would have chosen. And even further, it could work for any chi and psi that are related to each other through what are called the Cauchy-Riemann equations. I'll leave a link to those down below. Okay, so what we have now for our energy is this term is gone, and we're left with that. Grad chi squared plus grad psi squared. And no coupling terms between the rotational and divergent modes. So this is cool. Now I'm going to change gears here for a minute. So we have an expression now for kinetic energy. And then when you talk about spectra. So normally when you calculate a spectra, what we're doing is we're taking data and you project that data onto functions that you know, you have some knowledge of. Like, you know the length scales exhibited by a sine wave, right, with a given wave number. And when I say project, what we're really doing when you do a projection is you're quantifying how much your data is similar to that function you understand. We do this all the time with Fourier series. The thing is, Fourier series are periodic. The domains we're working with are not periodic, and nor is the data that's defined on those domains. We have islands and holes, and Fourier series in multiple dimensions only works with what are called tensor product domains. In other words, in 2D we have things that are logically rectangular. Now, you can do coordinate transformations and these kinds of things. But I'm going to show you a way you don't have to do that. The problem with having a set of basis functions like Fourier series that is not consistent with your geometry or the data that's there is you get artificial slopes in a spectra. And anyone who's studied spectral element theory or spectral theory for like numerical solvers will tell you that if you try to approximate a step function, for example, with Fourier series, the rate of decay of the spectral coefficients is going to be linear with the wave number. So you get a k to the minus 1 slope simply because you have a step function. And that in itself will tell you something about what's going on with the data. But like in turbulence theory, a lot of folks are interested in, looking at data that is smooth, and estimating the spectral slopes. It tells you a little bit about the dynamics, about what's going on in the fluid. And if you end up with an artificial slope simply because you're on a finite domain and your data is not periodic, it's going to contaminate your results. It's going to hide what you're really looking for. So we're going to work around that. So Fourier series, they come from a specific set of Sturm-Liouville problems. And remember, Sturm-Liouville problems are a way to generate basis functions. All right, you can think of them like that. The Fourier series come from the problem that I'm going to use. Actually, for Fourier, we'll use f. Del squared f is minus, we'll say lambda squared f. And then f is periodic on the boundaries. Okay? And there's a whole bunch of modes. So we have a whole bunch of lambdas, a whole bunch of f's that satisfy this interior equation with that boundary condition, and all of them are periodic on the domain A. We want to relax that. Now, if we go back a couple slides here, we have two functions, chi and psi, that satisfy these elliptic equations with Neumann boundary conditions and Dirichlet boundary conditions. So what we're going to do is, instead of using periodic boundary conditions, we're going to define two sets of basis functions. One that satisfies homogeneous Dirichlet and one that satisfies homogeneous Neumann. So the Dirichlet modes, so grad xi equals, we're going to say minus lambda I squared xi, and the xi on the boundary of A are going to be 0. Now we do need, when we're doing these basis functions, we do need homogeneous boundary conditions so that we have a good property known as orthogonality. I'll show you what that means here in a minute. So these are our Dirichlet modes. Okay. Now for general arbitrary geometries, there's not going to be a closed form solution for these guys. In fact, what we do in practice is we're going to calculate those numerically. We'll get there. Now the Neumann modes, I'm going to say del squared eta I is minus sigma I squared eta I. And the Neumann modes satisfy homogeneous Neumann boundary conditions. Okay. So with these modes, what we can do is we can write remember the divergent modes satisfy, so remember divergent modes satisfy this equation with inhomogeneous Neumann boundary conditions. Okay. And the rotational modes satisfy this equation with potentially inhomogeneous Dirichlet boundary conditions. And what we can do is write psi as a linear superposition, so I equals 0 to infinity. We'll call it psi hat I, so the hatted variables are constants, and those constants are called the spectral coefficients times Ci, and the spatial structure comes from Ci's. The chi's we can write as sum I equals 0 to infinity chi hat I eta I. And the spatial structure for the divergent part comes from the eta functions. So with Fourier, we knew if I had spectral coefficients for Fourier modes, so if the sine and eta were Fourier functions, so sines and cosines, we could attribute, what we typically do when we draw a spectra is we would calculate, these spectral coefficients, square them, and each value of I, so we vary I this way, this corresponds to a length scale, right? There's a length scale there. And then we would plot the kinetic energy at that specific value of I, and that would give us the spectra. And the length scale that we choose for the Fourier series is going to come from this guy. The length scale, if we just do the scale analysis, we have units of eta on both sides. Del squared is 1 over L squared, so that means sigma I squared has units of 1 over L squared. That means that sigma I to the minus 1 has units of length. Okay, so in some sense, the eigenvalues that come out of this problem give us a measure of length scale, and then the spectral coefficients that we'll talk about how to calculate here shortly will give us a measure of how similar the data is to each of these basis functions. And if we use this decomposition, we can calculate that specific mode's contribution to the energy. So we're going to show that real quick. We'll do the kinetic energy calculation first in terms of these spectral modes. Okay. And then what we're going to do from there is show how to calculate those spectral coefficients. So remember, kinetic energy is 1/2 grad psi squared plus grad chi squared dA. Okay. So if I calculate grad psi squared, that is going to be the sum over I psi I grad Ci. This is going to be multiplied by sum over J psi hat J grad Cj. Okay. And then by doing an area integral, I can pull the sums out front. Sum over I, sum over J, psi hat I, psi hat J, grad Ci dotted with grad Cj dA. So we need to figure out how to evaluate this integral. So I'm going to flip the page. Okay, so we want to calculate grad Ci dotted with grad Cj dA. We know that del squared Ci equals minus lambda squared, lambda I squared Ci. And we know that del squared Cj is going to be minus lambda j squared Cj. What I'm going to do is multiply this equation by Cj. Then we're going to integrate over A. And then on this first term, we're going to do an integration by parts once. Okay, and we're going to do the same thing down here, except we're going to multiply by Ci, integrate over A, and then do an integration by parts there. When we do that, we end up with Cj grad Ci dotted with n hat dA minus grad Ci dotted grad Cj equals, let's do integral dA, and this is supposed to be dl, line integral. So on the right side we have minus lambda I squared integral A Ci Cj dA. Now this first term is 0 by definition because the Cj are all 0 on all the boundaries. Remember, these modes have homogeneous directionally boundary conditions. So if we do this for the second equation, we get a similar result. If I have grad Cj dotted with grad Ci, which those commute, so this is the same thing. And on the right side, I have minus lambda j squared. Ci, Cj, dA. And if I subtract these equations from each other, so if I take this equation, subtract this equation, what I'm left with is lambda j squared minus lambda I squared area integral Ci, Cj, dA has got to be 0. So there's only two ways this can be 0. Okay? If I equals j, right? If I equals j, then this term goes to 0. If I is not equal to j, then we must have the area integral Ci, Cj, dA is 0. This is the orthogonality property. This is a very useful property for us. It makes a lot of the analysis we're going to do really easy. That's orthogonality. We can simplify this a little bit, just notationally. We're going to define what's called the inner product for this space. So if I have two functions, f and g, that's going to be the area integral of f times g dA. That's inner product. So orthogonality can be restated. Ci, Cj is going to be the Kronecker delta. So in other words, it's 0 when I is not equal to j, and when I equals j, it's 1, and it's going to be multiplied by the magnitude of Ci squared. And so, we get what's called an induced norm from this. So this notation, the magnitude is just, here, I'll write it in terms of f. So the magnitude of a function is f, that's squared, because that's magnitude. Okay, so we have that result. If we go back, we can take either of these equations, and we have an expression for grad C dotted with, we have an expression for grad Ci dotted with grad Cj. What we have is, I'm going to use the inner product notation, we have grad Ci grad Cj is equal to lambda I squared Ci Cj, which, because of the orthogonality principle, we showed that this was Kronecker delta Ij Ci squared. Okay, so we have that expression now. And you can show the same thing for the Neumann modes. Same thing works out there. So if we go back to our kinetic energy, what we get is sum over I, sum over j, c hat I, c hat j, delta ij, magnitude Ci squared. The delta ij means that only I equals j terms survive, and we're left with the sum over I, psi hat I squared, Ci squared. Okay. We're going to assume that the basis functions are normalized, which means that the psi I magnitudes are 1, and the eta I magnitudes are 1. Okay. Right, so then this just becomes, oh, I left out a term here. My lambda I squared. You know, still make mistakes. All right, so what we're left with is 1/2 times the sum over I. If we do this both for psi and chi, we get psi hat I squared lambda I squared plus chi hat I squared sigma I squared equals 0 to n. Now I am being a little bit sloppy. Technically, there are a different set of modes for these guys than there are for these guys. This really should be two distinct sums, because I can have all possible combinations of, like I can hold this guy fixed and vary all of these, and it gives me one direction of modes, and you can do it the other way. But I know what I mean when I'm writing this, so you just need to be careful. Probably not the best notation, but you know, trying to take it easy today. So that's our kinetic energy. Now each contribution to the kinetic energy, okay, fine, I'm going to do it. The way we're going to do this is as follows. I'm going to put a bracket here, parenthesis there. I'm going to run out of space. I'm going to kill this. And this is not the end. We're not doing truncation yet, which we will, maybe not today, maybe another day. Here what we have is the chi hat j squared sigma j squared. Okay, so that's our kinetic energy. This is a really important result because this shows we have what's called Parseval's equality. In other words, I can calculate the kinetic energy in space I can take u squared plus v squared, integrate over area, and get a number, multiplied by 1/2. Or I can project the divergence onto these modes, and the rotation and the vorticity onto these modes, and I get my spectral coefficients, and I can get an energy in that case by adding up the square of those spectral coefficients multiplied by the eigenvalues. So we call k j I is psi hat I squared lambda I squared chi hat j squared sigma j squared. This is the 1/2 out front, the energy density. So if I calculate those spectral coefficients for I and a j, The I and the j are associated with the length scales that correlate with lambda I squared and sigma j squared, right? If I take lambda I to the -1, sigma j to the -1, those could be length scales. I can tell you how much energy is at that length scale for the rotational and divergent parts. Of course, you can look at them separately. You can look at how much energy is associated with the rotational part only. Look at how much energy is associated with the divergent part only at a specific length scale. You can do a lot of things. So this is kind of neat. And we never had to assume periodicity. So this will work for arbitrary domain provided we can calculate those Dirichlet modes and the Neumann modes. Now the question is, how do we calculate these? Because there's a problem here. These modes satisfy homogeneous Dirichlet and homogeneous Neumann boundary conditions, but our original problems are inhomogeneous boundary conditions. So feels like those modes would have a hard time matching the boundary conditions of the original problem. So there's a trick. We're going to turn to Green's theorem. This stuff is pretty cool, in my opinion. All right, so a Green's function for the Laplacian operator satisfies del squared G is delta. This is the Dirac delta function, delta x minus x naught, some reference point. What that forcing is an impulse at a very specific point. It's got a very large value. Theoretically, it's an infinite valued function at that single point, and then it's 0 far away. So when you do an area integral over this thing, it sort of smooths it out, and you get sort of the influence of an impulse is what's represented by that Green's function. Now the Green's function, we're going to do a Green's function for the Dirichlet boundary conditions and the Neumann boundary conditions. The Green's function, we're going to have satisfy the same homogeneous Neumann boundary conditions for the Neumann case. And we're going to do some trickery. Just like we had done to prove orthogonality, we're going to basically follow some similar steps here to show what's called the Green's function solution to the inhomogeneous, so the Poisson's equation, so inhomogeneous Laplacian with inhomogeneous boundary conditions. Okay, so remember, we have the Green's function here, G satisfies this equation, and then we also have our divergent modes. The divergent part of the flow is going to satisfy this boundary value problem. Right? Okay. So what we can do is multiply the interior equation by G, integrate over space, and we'll apply integration by parts once on that first term. So what I end up with is G grad chi dotted with n hat dA minus grad G dotted with grad chi dA equals G d dA. This is again L, and this is a line integral, this is an area integral. And we can do the same thing up here. Except here we're going to multiply by chi, integrate over space, and do an integration by parts once on that first term. I love the patterns. Oops. here we have chi, delta function x minus x naught, dA. And if you remember the delta function, what it's going to do is cherry pick out whatever the thing is we're integrating against, evaluate it at this specific point, x naught. Okay. Now because of the boundary conditions for the Green's function, this goes to 0. Okay. So now if we subtract these equations, we take the first equation, subtract from the second one, we have is boundary integral g grad chi dotted with n hat dl. This term and this term cancel. We have a Green's function multiplied by the divergence of the velocity field, integrated over space, minus chi at x naught. Okay. So we're pretty close to having our solution here. We're going to substitute in the boundary conditions for chi. This is going to become the normal velocity. And we're going to rearrange some things. I'm going to move chi to the left and move this term to the right. So what I have is chi at the point x naught is going to be equal to the area integral of g, and I'm going to denote g as being a function of the parameters x and x naught, okay, multiplied by d, which is a function of x, dA, minus boundary integral g, x, x naught, u dot n hat dl. Now we're going to do a clever trick. You ready for it? We're going to write g x x naught as sum over I, 0 to infinity, g hat I, which is going to depend on x naught. So the spectral coefficients here are going to depend on that position. And we're going to use the Neumann modes. The Neumann modes were the etas. And if we go back to the equation for g and I substitute this in, what I get is sum over I, g hat I, I'm going to leave off the dependency there, I get del squared eta I, it's got to be equal to delta x minus x naught. Okay. Now remember, del squared eta I, we can just write as minus sigma I squared eta I. Okay. That's still equal to delta x minus x naught. And what we can do now is multiply this whole thing by eta j and integrate over space. Pull that minus sign out front. sigma I squared, eta I. If I do that, right, what I have is a dot product, or an inner product, eta I, eta j, and we get the inner product of delta with eta j. Cool. And remember, this is just the Kronecker delta, so only I equals j survives this, and I'm just left with minus g hat j sigma j squared equals eta j at x naught. So as long as the eigenvalue is not 0, as long as the eigenvalue is not 0, what I have is g hat j is going to be the negative eta j at x naught over sigma j squared. See where we're going with this, right? Let's clear some space. And now that we got this, let's go ahead and plug in our series solution for G with the components that we, with the spectral coefficients for the Green's function that we found. So what we have is chi at x naught is going to be, so we have the sum over I we have minus eta I at x naught over sigma I squared. So we have the inner product of D with eta I. And then what I have left over is again minus. And we have a minus again. In fact, what I'm going to do is go ahead and pull these coefficients out front. So we get a minus, and we're just left with a boundary integral of eta I of x u dot n hat dl. Okay. And if I want to, I got this parameter here, x naught. I can swap that out. I can write chi of x is the sum over I I'm going to rearrange things just a little bit. So, I'll put that minus sign up front. Minus sign out front. And I have the projection of D onto eta I. So the projection of the divergence field onto eta I. And I subtract the boundary integral, partial A. And then we have the normal velocities on the boundary, eta I, dl. Okay. And this is divided by, I'll just say sigma I to the minus 2, eta I of x. Now, remember, what we were after was this representation. So what this means is that the spectral coefficients are negative projection of D onto eta I minus boundary integral u dot n hat eta I dl sigma I to the minus 2. So we have our spectral coefficients for the divergent part of the flow using a Green's function solution and a series expansion on the Neumann modes. And we can do a similar thing for the Dirichlet modes. And there, the Green's function, so again, this is Green's theorem. We have del squared h is delta x minus x naught. And then we have h on the boundaries is 0. So that's our Green's function for the Dirichlet modes. And remember the Dirichlet component, or the divergent part of the flow, says, or sorry, the rotational part of the flow satisfies del squared psi is vorticity, and psi on boundary, I need to be careful with my numbering here, so I'm going to call this k. Delta AK is going to be CK. When we do this, and we follow the same steps that we did before, what we end up with is the CI's are the negative of the projection of the vorticity onto CI, plus, and now we have a sum over all the islands, the little boundaries. So let's say there are, there's n of these boundaries, so k equals 0 to n. We have a boundary integral over each of those little boundaries, so the outer boundary and all those little islands. We have the CK, and we have grad CI dotted with n hat dl. And then we have a lambda I to the minus 2. So that's those coefficients. We do the same thing here. So let's summarize a few things. Because then we're going to, next time, take a look at some example problems that are fairly simple that we can calculate what those eigenmodes are and show how this works in practice, and then we'll start getting into some numerical problems. That'll be fun. Okay, so we have a 2D velocity field, and we wrote it using a Helmholtz decomposition, which allows us to say that u is gradient of chi, one potential, plus z hat cross grad psi. And again, this is our divergent part of the flow, and this is our rotational part of the flow. When we do this, we get two equations. Del squared chi is the divergence of u, which is d. Okay. And we chose the boundary condition such that the normal gradient of chi matches the normal velocity. We have the equation for psi, the rotational part, so del squared psi is the vorticity. And we have the boundary condition that on each of our boundaries, psi is some constant. Okay. Our solutions, our series-based solutions, chi is sum I 0 to infinity, chi hat I, and these were the divergent part of the flow is a linear superposition of Neumann modes. And the Neumann modes here are eta i's. And the rotational part of the flow is a linear combination of Dirichlet modes. Okay, so those Neumann modes satisfied. Minus sigma I squared eta I grad eta I dot n hat on the boundary is 0. And the Dirichlet modes satisfy del squared ci minus lambda I squared ci. And the ci on the boundaries are 0. Each of these independently have the property that they are mutually orthonormal. So again, what that means is the inner product of eta I, eta j is 0 unless I equals j. And when I equals j, it's the magnitude of those functions, and we've chosen the magnitude to be 1, so we've normalized them. They're orthonormal. We have ci, cj, again, delta I, j. Okay. And then we've done Green's function solutions to the original problems. And we've expressed the Green's functions as linear combinations of the Dirichlet and Neumann modes appropriately. And when we did that, we found that the spectral coefficients that we have are negative, and I'm going to call this di minus boundary integral of u dotted with n hat multiplied by eta I dl sigma I to the minus 2 and then psi hat i's are negative. Call this zeta I minus, it's actually going to be plus for this one, plus sum over k equals 0 to little n. This is the sum over the boundaries of our problem, partial ak, ck, and we have grad ci dotted with n hat. dl. And then here we have lambda I to the minus 2. So these are our spectral coefficients. Last, we have an expression for the kinetic energy. So remember, this was 1/2 integral of u squared plus v squared dA. We can also write this as, this was a sum over I, 0 to infinity, psi hat I squared, lambda I squared, right? Plus the sum over j, 0 to infinity, chi hat j squared, sigma j squared. Okay, so that's what we had for the kinetic energy. So that's where I'm going to leave it today. These are our final results for today. Next time, tune in, and we will go through some hand calculations for some simple domains. The first one I'm going to do is one in which you probably could get away with doing Fourier series, square domain, but not periodic boundary conditions. So that'll be an interesting one. See you next time.